Now, what we're going to talk about next is what is a resistor. So a resistor is anything that is going to be deliberately, well, not necessarily deliberately, but it's going to be anything that gets put in the way or gets in the way of our current flowing. The biggest thing that we use is what the device that we call resistors. So what we have is resistors. They can be a couple of different things. The majority of the ones that we're going to be using are going to be a carbon film style of resistor. So what this means is this resistor is made out of carbon, which has been doped to allow a certain amount of current to flow through it. Basically, we've put a lot of carbon in there, which doesn't transfer its electrons very easy. And so we have this idea of this carbon in here. We're going to dope it with some material to let more electrons flow through it. When it allows more electrons to flow through it without being impeded, we call that a conductor. So a conductor is a material that allows electrons to flow. An insulator blocks electrons from flowing. So it uses materials that has full valence shell electrons, things such as like wood and glass and air and stuff like that. They don't allow electrons to flow freely. Conductors are usually metals, copper, gold, silver, things like that. So we have a conductor and an insulator. The resistor is a semiconductor part that's manufactured that allows so many electrons to flow. It controls how many electrons flow. So a resistor controls electron flow. It doesn't just stop it, doesn't just allow it to go through. Generally, these are the types of resistors that we're going to see. In the lab, you're going to see resistors that look like these guys, and these ones, and those ones, and these ones. Okay? Those are the styles that we have. All they are is just different materials of what they're being made out of. So how do we determine what a resistor is? What is its value? How much is it going to restrict or block off electrons from flowing? So as we talked about, this is what we call resistance. It's this numerical value of how much it opposes the flow of electrons. Well, what we get is we're going to get a section of colors, as you can see on these bands, to determine what their values are. So this is our color code for the resistors. Now, our color code is going to look very similar to this. A lot of the times this is going to be shifted one way or the other. So these 3 or 4 bands right here that sit here, sometimes they're going to sit a little farther over, and there's going to be a bigger gap between the 3rd and the 4th band to help you identify which one's which. Another trick that we'll see is this tolerance band will usually be sitting right on the little nub of this. Also, you'll see when they make these, they look kind of like a dog bone. They come up and go down and back up like this. It's either a smaller little hump on the one side, or it's just a thinner hump. So we might have a wider one, or we might have, different sizes on those, but generally the bigger side is going to be where our numbers start. The thinner side is going to be, or not as tall side is going to be the multiplier or the tolerance rating of our resistor. So the way this works is we have these color bands. So up here we have a 4-band resistor. Down here this is a 5-band. And we will talk about both styles as we get going. But they are solved the exact same. So what we look at is in our 4-band is our colors. So on this resistor, it does tell us what we have, but we have a brown, a red, brown, and a gold. So what we have to do is determine what our color code is telling us. These first 2 digits on a 4-band is going to give us the value of this number. So brown, when we come over here and look, correlates to number 1. Red correlates to number 2. Brown, again, correlates to number 1. And then our last one is our tolerance, basically how far can this thing be before it's considered out of spec, is gold. So if we look down here on this list, gold is a 0.1. which is right here on this side, that's a multiplier. That's something else we'll talk about in a minute. The gold is the tolerance, which is 5%. So that means that this resistor can vary 5% and still be considered good. So we look at our values. We've got everything decrypted. The first two is the value that we start with. So those are going to come down. So I get the value of 12. Then I'm going to multiply it by a power of 10, and this one is my power, my multiplier. So this becomes 12 times 10 to the first, and my tolerance is plus or minus 5%. So then I go back through, and this is in scientific notation, or it's in a number notation. It's not necessarily scientific. We want to put it in terms of engineering notation. So we need to convert this power of 10 so it's divisible by 3. The easiest way to do is to make this power, reduce it down, times 10 to the 0. So if I make my power smaller, my number has to get bigger. So we get 120 times 10 to the 0 plus or minus 5%. 10 to the 0 is 1, so I'm left with 120 ohms plus or minus 5%, which is great. Now I know what it's supposed to be. So now when I get one of these and I go to measure it, I hook it up, and it's going to measure the resistance. So we're going to be sending a specific amount of current through this component, and we're going to measure how much current is actually moving through it. This is going to then determine the resistance based on those values. So what we get is we have to look at our value. So 120 ohms is our nominal value. This is what it should be. My tolerance is 5%. So we need to take this percent and turn it into numeric form. So what I'm going to do is take my 5%. So I'm going to take 0.05 and I'm going to times that by 120. So 120 times 0.05 is equal to 6 ohms. So that means my value is 120 ohms plus or minus 6 ohms. So now I can take my nominal, I have my tolerance value, and then I can solve for my min and max. When I measure it, that way I have an idea of what it should be. So I've got my max is going to be my nominal plus my tolerance. My minimum is going to be my nominal minus my tolerance. So what I get is 120 plus 6, which gives me 126 ohms for my max. My minimum is 120 minus 6, so that gives me 114. So now when I go to measure this resistor, as long as it measures between 126 and 114, it is considered accurate and correct and good. So the other thing I can do if I want to find these mins and maxes without having to do these extra steps, I can solve it by my max going like this. I take my nominal and I incorporate my tolerance into my decimal to multiply it. So I multiply that by a 1.05 because my 0.05 was my tolerance. So I just add that to 1. That's going to give me my 126. My minimum, I take my nominal and I multiply it by 0.95. With 1.0 being 100, I go up 5% or down 5%, and that's going to give me my 114. So either way, there are my options to get my min and max. And this will work for any kind of these resistors. You have four color bands, gives you 4 digits. Your first two is the value, the starting value. Your third one is your multiplier. What are you multiplying that by? Your first two values, and then your tolerance. A 5-band does the same thing, but what it does is it gives you a third digit. So down here, what this does, if we look at this example, we've got a yellow and a violet and a black and a brown and a brown. So my yellow is 4, my violet is 7, black is 0, and then times 10 to my brown, which is 1, and my brown again is the tolerance, so I look over here, and this one is 1%. So then when I carry this through and put this in proper engineering notation, again, I want this to go to a power of 3. 0 is going to be my closest power of 3. So I'm going to move this value smaller, which means I have to increase this. My power goes down, value goes up. So I get 4,700 ohms plus or minus 1%. But again, in proper engineering notation, this isn't in proper engineering notation. So this might have been the easier way to go, but as far as engineering notation goes, we went the wrong direction. So instead of taking this down to 0, we need to take this one up to 3, which is going to be our kilo. So that means this goes up 2 spots, which means this number has to get smaller by 2 spots. So I get 4.7 kiloohms plus or minus 1%. So here's my nominal value. Either one is correct. This is an engineering notation. This is where we want it displayed. This number is easier to work with on your calculator. And I want to find my range, my min and my max value of this resistance. So I take 4,700 or 4.7K times 0.99, because 1% is the same as 0.01. And I'm going to take my minimum to find this is 4,700 times 1.01. This gives me my min. This gives me my max. And then when I do my math and my conversions, so 4,700 times 0.99, this gives me 4,653 or 4.653K. And then my max is 4,700 times 1.01 is going to give me 4,747 or 4.747K. So there's my min, there's my max. Oops, not min again, max. So there's my values. So that's how I use my resistor color code to determine the values of these resistors. Now, going from your color code to your value is pretty easy. It's right there ready to go. But part of the problem is maybe I need to go from a value and I need to find a resistor. Okay, so we'll scroll down a little bit so we can still see this. So let's say I need to solve for a value. So let's say I need a 6.2 mega ohm resistor and I want to make sure I have it as a plus or minus 10%. So pretty far out there, but we can tolerate that. So same things I'm going to look. I'm going to write this number out in numeric form instead of engineering notation with its prefixes here. So I'm going to go 6.2 times 10 to the 6th plus or minus 10%. So now that I'm looking, I need to get this back into 2 digits so I can report it if I'm going for a 4-band, or 3 digits if I'm going for a 5-band. So this one, we're just going to make it at two digits. So I'm going to take this up from 6.2 to 62. So I made my number bigger, so my power has to decrease. It has to be smaller to balance it. So I get the 5 plus or minus 10%. Now I have my 2-digit code, my power, and my tolerance. So I can look, 62 is going to be a blue, 2 is going to be red, 5 is going to be a green, and 10% tolerance is going to be silver. So when I'm looking for a resistor, if I have a pile of them sitting in here, kind of like this, sitting up there in that group, now I'm going to be going through and I say, I need to find a blue, red, green, silver resistor in my pile of resistors. Now, depending on what application you're looking at, the tolerance is going to play a big part of it. Most of the resistors that we are going to be using are going to be this gold or silver band, this plus or minus 5 or plus or minus 10% values. Gives us a fairly good range of values. Some of the other things we could be looking at is with this brown resistor right here, this means it's good within 1% or it's manufactured to be 1% out. You're going to pay a lot more money for a 1% than you would a 5 or a 10%, but maybe you need that accuracy. If you don't need it, use the cheaper parts. Some of the other tolerances that you're going to see, orange doesn't use one, yellow doesn't use one, green is a 0.5% tolerance, blue is a 0.25% tolerance, violet is a 0.1% tolerance, and gray is a 0.05% tolerance. So again, depending on your application, if you have to be super accurate with these values and you want a 120 ohm resistor to be 120 ohms when you pull it out of the drawer, you need to get one with a higher resistance. Like I said, this is normal. Normal everyday stuff. You get down in here into these values and 1%, 0.5%, you're going to be looking at these two guys. This is military, because those need to be super exact and super repeatable. You just need to have one value to throw in. You don't want to make 6 measurements. When you start getting into this gray and violet area, this is NASA. Okay, for example, they have to be super, super accurate when they're sending things out into space because they can't fail. They can't have variations to them. They have to be able to just plug and play and say, this is the part and it has to work. Because when you start talking about a NASA scale, which is this, they mostly study what is very, very big or very, very far away things, they have to be very, very, very precise. The more decimals off that you are, the bigger your swing is going to be when you start looking at long distances or large values. So a lot of like NASA or government work or even scientific work is going to be using these 0.5s. But again, comparing costs, these 5 to 10 cent resistors are going to cost anywhere between 1 cent. Usually we can get them for like 6 cents. Okay, these military ones, these are going to be in the 50 cent range, just for example. This really, really high tolerance one, they're going to be military, because I erased it. We're going to be looking at 50 cents. Okay, and then the other one is you start getting into these scientific ones. This resistor here with these accuracies, you're going to be looking at examples of $2 to $5 a piece. So depending on, or more, depending on your production scale. So if you want things to be super accurate, you're going to be paying for it. And then that cost has to be absorbed somewhere. So again, what we're going to be dealing with the majority of the time is this normal range. They're between 1 and 6 cents a piece. 5 and 10% is just fine for what we are after. And now you should be able to go back and forth between either the 4-band or 5-band and being able to say, hey, here's my color code, what's my value? And if I need to, I'm looking for a specific value. Here's the value I need. Here's the colors that I need to find. And you'll be using this quite a lot, especially with your resistor kits and going from project to project. You might have a big box of them, things like that. So that is what we're after with these values and trying to find the resistance. So again, this is kind of the second half of it. Following with what's going on with the electron, this is the physical resistor that we're going to be using in class and in lab.